Welcome to this explainer. Today, we're diving into something that is, honestly, a total breakthrough for anyone building AI applications. We're going to see exactly how Headroom takes the old, clunky rolling window approach to LLM context and completely transforms it into a dynamic, learning-based curation system. It's called Intelligent Context, and it is quite literally changing how machines remember. So, right off the bat, what happens when your LLM just forgets? We've all been there, right? You're deep into this really complex workflow, and suddenly the AI just starts acting like a blank slate. It completely ignores your core instructions. Well, this is a massive headache known in the industry as chronological amnesia. Basically, your foundational instructions are getting dropped purely because they're old when the model inevitably hits its token limit. No logic to it, just it's old, so toss it.
Let's contrast this frustrating old way with Headroom's new approach. The old way is basically naive chronological dropping, just a blind conveyor belt straight into the trash, first in, first out. But the new way, Intelligent Context, is totally different. It uses importance-based dropping. It intelligently evaluates your data and drops the absolutely least valuable information first. This means it actually preserves what matters, regardless of when it entered the chat. Here is our quick roadmap for unpacking how this architecture actually works under the hood. 1. The context window problem. 2. Enter intelligent context. 3. The 6 scoring weights. 4. Built-in protection rules. And 5. Learning over time. Let's get right into it.
Section 1. The context window problem. Okay, so when token budgets are exceeded, standard models naively delete the oldest messages, causing that chronological amnesia. This is just a recipe for catastrophic failure. Why? Because older does not mean less important. Imagine losing your absolute most crucial system prompts or your output formatting rules just because a user talked too much or an API returned a massive wall of text. The model totally loses its anchor. It starts spitting out raw JSON when you specifically ask for Markdown. It completely derails the whole experience.
Section 2. Enter intelligent context. So Headroom gives us intelligent context as the fix. Think of this as a super smart message-level compressor. It scores message importance and then drops the lowest scores to CCR for LLM retrieval. What does that actually mean? It means that dropped messages aren't gone forever. They go to CCR, continuous context retrieval. If the AI suddenly realizes, wait, I actually need that old data to solve this, it just pulls it back on demand. It's compression without permanent deletion. Best of both worlds, really.
Section 3, the 6 scoring weights.
Let's look at the actual math here. These 6 automatically normalized factors are basically the recipe for AI memory. First, two-oin importance is at 25% for learned retrieval patterns. Recency gets 20% with an exponential decay, so newer stuff still matters. Semantic similarity is another 20%, meaning if you loop back to talking about databases, old database messages get bumped up. Error indicator sits at 15% to preserve vital troubleshooting steps. Forward reference is 15%, protecting messages that others depend on so logical chains don't break. And finally, token density at 5% favors unique info over repetitive fluff. But notice that absolute heavyweight champion at the top, two-oin, at a massive 25%. We really need to zoom in on that top weight. TOIN stands for the Tool Output Intelligence Network. It's a system that learns across all users to score messages higher if they match patterns frequently retrieved via CCR. It is the heavy lifter. If users across the entire network constantly need to pull a specific type of dropped output back into context, TOIN learns that exact pattern. And then it just automatically starts scoring those specific messages higher right out of the gate, making sure they don't get dropped in the first place.
And this just brilliantly illustrates how flexible the system is. Error detection relies on 2N's learned field semantics, inferred type. What that means is it completely eliminates the need for hard-coded keyword matching. There are 0 hard-coded rules here. It doesn't just blindly scan for the word fail. It adapts to what an error actually looks like in your specific data patterns, preserving those critical messages. And honestly, not having to write endless, messy rejects for error catching, that is a massive quality of life win for developers.
Section 4. Built-in protection rules. Now, you might be thinking, what if it accidentally drops my system prompt? Well, Headroom has strict built-in protection rules. First, output buffer reservation guarantees there are always tokens saved for the model's actual response. Second, system message protection means your core instructions are absolutely immune to being dropped. And third, turn protection safeguards your immediate conversation, defaulting to preserving the last 2 turns no matter what the math says. It's an absolute baseline of stability.
And hey, if the scoring data is ever temporarily unavailable, there's a really solid fallback rule set. It acts as a safe baseline. It will drop the oldest messages first, but it still always keeps the system prompt and always keeps the last n turns. Crucially, though, it drops tool calls and their responses as atomic pairs. This ensures you never end up with orphaned data, like an answer just floating around with the question it belongs to, which is a huge cause of confusing model hallucinations.
Section 5, Learning over time. So intelligent context isn't just a static algorithm. It actually grows. Let's trace this incredible feedback loop. Step 1, messages drop based on current scores. Step 2, dropped messages are safely stored in CCR. Step 3, the LLM eventually realizes it needs that specific dropped data to debug something, so it retrieves it. Step 4, Toyn sees this happen and records that exact pattern. And step 5, future similar patterns automatically score higher. Through this loop, Toyn literally learns to keep those frequently needed error messages while aggressively trashing unhelpful success logs that nobody ever looks at anyway.
And here is the absolute bottom line. Drop accuracy improves across all users, not just within one session. Think about that network effect. The system literally gets smarter, more efficient, and more precise the more it's used by everybody. Your AI's memory is actively crowdsourcing what actually matters. I'll leave you with this provocative thought to challenge your current architecture. Is your AI's memory getting smarter, or is it just getting full? Because if you are still relying on a naive rolling window, you're just filling up a bucket and letting your most important, oldest context spill right over the edges. It's time to stop settling for chronological amnesia. Thanks so much for joining this explainer. Keep exploring and keep optimizing.